Good morning to all. The rheology in bioprocess engineering. So, last class we discussed about the type of non-Newtonian fluids in bioprocessing, but what are the different type of non-Newtonian fluids here, that we will see thoroughly here one by one. The first one is for the pseudoplastics. The pseudoplastics, sometimes we can always say shear thinning of the fluids. So, these are different type of non-Newtonian fluids and how we are going to use in the bioprocess reactor and bioprocess this one. So, we will discuss all here. So, the pseudoplastic we can always call as shear thinning of fluids or pseudoplastic of fluids here. So, the viscosity, whenever the viscosity decreases, the shear rate get increase. Okay, the shear rate will get always increase here. When viscosity decrease, the shear rate increase here. So, the same here, the molecular, whenever if apply under shear, the molecular alignment and the structure, definitely they will get a breakdown when you apply shear or remove the shear, whatever here. Okay. So, the common model here, the model is here tau equal to k, this is a shear rate. Okay. We always say okay, the tau equal to k shear rate, the n is a stands here, the base whether n is a less than 1 or greater than 1 here. So, always here n is a less than 1, this is a normal, the model used for the pseudoplastic here. So, what are the examples, the bioprocess example fall in the pseudoplastic fluids here. So, the fungal fermentation broth, especially the aspergillus and the penicillium, all come under the pseudoplastic, the example of here. Then the xanthan gum, then alginate solutions. So, all will come in the bioprocess, the example here. So, another one, the best example for the cellulose containing plant cell cultures. So, these are the three under fall in the pseudoplastics. So, whenever if you increase the shear rate, the viscosity get decrease, either it is the fungal fermentation broth or xanthan gum or alginate solution, so or cellulose containing plant cell culture also. So, what are the engineering implication for here? So, whenever this the impeller here, the near the viscosity always very low, definitely you will get the improved mixing. So, that is only lower viscosity, the near impeller, the improved mixing will be there. So, whenever the high viscosity, wherever the low shear, the viscosity is high, and then definitely the oxygen transfer limitation, we always say OTL, oxygen transfer limitation will be here. So, the first one is we discuss about the pseudoplastic fluids here. The next one, the Bingham plastic fluids here. The same way, if you draw with the shear stress, one is the here shear stress tau, then shear rate and the shear rate here. Then the tau equal tau naught. So, the until that one there is no flow, that is the meaning here. So, it is an example here like tau equal to tau naught, there is no flow, but only if you cross or exceed the tau naught, the shear stress, then the flow starts. So, that is called a Bingham plastic here. So, but after yielding, once they get the point, then it behave as a Newtonian fluids. Newtonian fluids, suppose you know the shear rate and then the shear stress or whatever the or shear stress versus velocity gradient very linearly, that is fall in the Newtonian fluids here. But again the example of the Bingham plastic here, what are the example of Bingham plastic here? The concentrated yeast slurry, this is one of the best example for here. Then activated sludge process in the wastewater, the bioreactor. So, we will always use the activated sludge process in the wastewater treatment. Then highly concentrated microbial paste, these are the example under the Bingham plastic here. So, here what engineering implication here we need here, so requires a minimum impeller torque to initiate the flow, otherwise we cannot start the flow. Say when I want to start the flow, you need minimum, otherwise this like it never gets started that one. I will explain maybe with the forthcoming slide very neatly how the minimum the torque we have to give here. So, it requires a minimum impeller torque to initiate the flow, we have to use this one. Then other one is for poor mixing at low agitation speed. Whenever the agitation speed is very less and there is no mixing, the mixing is definitely it's a big issue here. So, this all coming in the Bingham plastics. Other is a caisson plastic fluids here. So, here I already explained up to tau naught, then that behave as a Newtonian fluid. Say example here up to here it behave as the previous one Newtonian fluids here, but this behave as a non-linear. That is the only difference between the previous one and this one, and the previous one it behave as a Newtonian and the other one is the behave as a non-linear, either increase or of course it should get a decreaser one. So, that is a Kazan model here. The best example here, I mean before that the equation here, the shear stress the tau equal to, we will always write root tau equal to the tau naught, that is the initial, if it cross only then it will behave as the Newtonian fluids, the tau naught the shear stress here. So, then again the K into the shear rate we always write, okay, gamma shear rate here. So, what is the example for here, we use here the blood, the biomedical, definitely the relevance, the blood sample will when you use here that behave as a Kazan plastic model. Then the chocolate like lipid protein dispersion. So, there also this will fall in the bioprocess example, and then highly structured in the fermentation broth. There also this type of the fluids here under the category here. So, what are the engineering implication here? Definitely this is a complex the stress distribution, because it is more this one, then it is very important for the biomedical, because if you talk about the blood and this one, of course, the biomedical is the main thing here, then food processing here, because here already we have discussed the chocolate this one. So, then the food bioprocessing also very important here. So, these are the three type of different model I mean the non-Newtonian fluids here. Other one, the just for how we are explaining more how the Newtonian non-Newtonian fluids with very this one. So, the first one we discussed Newtonian, I just take the first point Newtonian. Though, so shear stress the shear rate, okay, the gamma, this is a gamma we will always shear rate, then the shear stress, you just see here it is very linearly, that is the reason it is called as the Newtonian fluids. So, the best the equation here tau equal to mu then okay gamma rate shear rate. So, the shear stress okay the proportional to shear rate, the shear stress proportional to shear rate here. So, the mu is a constant, the viscosity that we always say apparent viscosity, already we discussed in this one what is apparent viscosity. So, here mu A equal to for this one mu. So, here you just see the shear stress shear rate it is always get linear. So, this is always we call as a Newtonian, and here also the n equal to 1, that is the reason this is a Newtonian here. So, other one we discussed okay pseudoplastics, the example also we discussed the pseudoplastics. Again same way, this is shear stress tau, then there is a shear rate, okay. Of course, the apparent viscosity will come here, this point apparent viscosity here, but it behaves as a whenever the shear rate whenever get increase, but the shear stress get decrease, this point. Just see here the shear, whenever shear rate getting increase, but the shear stress get decrease, that is only the shows like this point, okay. I will one second maybe I will explain to you this way, okay. So, whenever the shear, this is a shear rate, we always write shear rate, then other one is for shear stress, okay. So, here when you increase this one, what will happen here, it is getting increase, when you getting increase the shear rate, but this shear stress get decrease. So, here always n is less than 1. So, this we used to call as pseudoplastic. Then other one is the Bingham plastics, okay. The Bingham plastic here the same way shear, this is a shear rate and other one is for shear stress here, but up to tau naught nothing happening here. You just see here when you increase the shear rate, but nothing happening, but once you reach the tau naught, then this slowly is getting increase, but it behave as a Newtonian. You just see because up to that behave as a non-Newtonian, but once you reach this point, then it behave as a Newtonian fluids. So, here this point, okay, it behave up to this is a non-Newtonian this one, but once you reach from this point to this point, then it behave as a non-Newtonian. So, there is a equation tau equal to tau naught, then the Kp, then gamma, this is a shear rate. Same way here, when the decreases, the shear stress decreases when increasing the shear rate, okay. So, this is equation for apparent viscosity, I just here also provided apparent viscosity we can get from here. The first point apparent viscosity mu A equal to mu. So, the last point is a Kazan plastics, same way here, but the only here up to tau naught it remains same, but here it get decrease. Okay, it get decrease here. That's only the shows curve like this. Okay, after some point the get decrease. The previous one it behave as a Newtonian fluids here. So whenever the shear rate get increase, initially there is not that much response, but once start to increase, then it's automatically getting decrease. So this is the equation, the tau, the shear stress, tau, root of tau equal to root of tau naught, then the Kp gamma, this one same whatever explanation here, again apparent viscosity. So this we took a reference book here, but just it is the 4 different type of fluids here. The one starts with the Newtonian here, very simple. Newtonian is the shear stress equal to shear rate, but you want to remove the proportionally constant, the mu is the viscosity. But here the pseudoplastics, but the same way here, but the equation is different, it is a n minus 1, but here n is always less than 1 for pseudoplastics. So Bingham plastics, so up to that some points nothing happening, then when you increase the shear rate, then the slowly get increase here. So this behave as the Newtonian fluids, already we discussed here also. Then the Kaysen plastic here, tau naught same way, but it behave as a non-linear. I already discussed, no, the first point is a linear, it's a linear point, but when you come here, it's behave as a, I just erase it, then you can get it. Okay, yeah. So if now it's a behave as a, see here it's behave as a non-linear, because when you increase the shear rate, it's getting this one. That's only the previous point we discussed that it behave as a non-linear, the forced yield behavior here. Okay, whenever this one, but the previous one we mentioned like a linear, after behave as a Newtonians. Okay, I think you understand that one. So then so far we discussed different type of the fluids here. Let's start with the Newtonian, then pseudoplastics, then Bingham plastics, then Kaysen plastics. So what are the examples? Because we need some examples, no? Newtonian we will take all type of gases, normal gases, then water. Okay, so then dispersion of gas in water, then low molecular weight of liquids, no, low molecular weight liquids, even high molecular weight we should not use, only low molecular weight of liquids, then some aqueous solution for low molecular weight compound. These all come the category of Newtonian fluids. So there is a shear stress that is proportional to shear rate. So here n always stand 1 here. So then for non-Newtonian also different type of examples are here. So only the pseudoplastics, here you can say pseudoplastics, the Bingham plastics, then Kaysen plastics. The pseudoplastics examples are here, the rubber solution what we use here, then polymer solution, some greases, some type of greases, starch suspension, no, they are also coming under the category of the pseudoplastics, the type of fluids. Then cellulose acetate, we always use this one. Some papers, bulb, okay, paint, some paints will always use there. Then wallpaper paste, some biological fluids, all come in the under the type of the pseudoplastic fluid here. The examples of here. So next one is the Bingham plastics. The Bingham plastics, some plastics are melt. So this all come Bingham plastics. Then whatever we are using, the cooking fats, same way for toothpaste. Then some soap and detergent, slurries, paper bulbs. See the toothpaste is the very best example. I will just, okay, when you want to use the toothpaste, initially when you use the apply pressure, the toothpaste will never come outside. But once you reach the limit, then it flow like a Newtonian fluids. That's the best example toothpaste. Normally we use for different type of toothpaste, no, in the morning. So the toothpaste here, why behaves the Bingham plastics? I will show you maybe the again. So up to this you apply pressure or whatever shear rate, but nothing happen. So once they reach the point, then the flow like very uniform. So that's the best example for the toothpaste will come as a Bingham plastics. Then the Kaysen plastic here, what we discussed, the blood, then okay, the tomato sauce, orange juice, then chocolates, even our printing ink, no, we will use for printers ink, all they come as a Kaysen plastic here. So we took reference book from this one for different. What we discuss here, the different type of Newtonian, non-Newtonian fluids with this example. So, it is very easy to understand for you how the examples, okay, the working with respect to the different type of fluids here. So, why non-Newtonian behavior matters in the bioprocess engineering? Because now why we have to study that one? Because if it non-Newtonian fluids, no, it directly affect the power consumption in the sterile bioreactors. Okay, because whenever we use the bioreactor, if it non-Newtonian, no, so there is a power consumption problem. So that we have to look very important that one. That's only directly affect that one. Always we discuss of the oxygen transfer coefficient. Okay, already we also we discussed very basic here. So this also directly affect oxygen transfer coefficient if it non-Newtonian fluids here. Then the shear, the sensitivity of cells, because the cell, the shear when it gets this one breakdown or whatever, if it non-Newtonian, definitely that will be very sensitive here. So you want to scale up, example from lab scale to you want to make a pilot scale, the scale up definitely when it is non-Newtonian, then we have to look at the how to lab scale to pilot scale. So if it non-Newtonian fluids, definitely we have to look at the what other parameters, other variables are getting disturbance here. So if you say example, sometime when you want to solve some modeling problem, we always assume like instead of 3-dimensional, we will always like 1-dimensional we solve, because that is very easy to solve. So most of them we used to do, say example, if you want to solve x, y, z direction, you need more boundary condition and more initial condition to solve the problem. To make our life easy, what we always do, we will only take a one direction, what is happening, so then we will solve that one. Same if here also, why you want to solve non-Newtonian, always we go for like a Newtonian, then we will solve that one. When you do Newtonian fluids here, but there is a under prediction of power requirements, because the system behave non-Newtonian, but you are assuming Newtonian, definitely you do not know how much the power requirement we need here. Then sometimes overestimation of mass transfer rates, it is a reverse way. Okay. So we assume that this mass transfer rate is overestimation when it is Newtonian fluids, but at the real case it is not happening that one. So then what is the accurate, the rheological characterization essential for here? The bioreactor design, when you want to do bioreactor design, we need more thorough knowledge of that one. Then the process optimization, the what we discussed industrial scale up. So these are the problems for when if it is non-Newtonian fluids, but when we assume as a Newtonian fluids, then we always assume a different way to solve, but if a real case is a non-Newtonian fluids. So that is the reason these are the effects if you want to do higher scale, that is lab scale to pilot scale studies. So then next is the 2 parameters rheological model for non-Newtonian fluids here. So many non-Newtonian fluids, okay, we have the equation already I discussed to you, maybe again we will discuss also. So only here the 2 parameters are 2, one is the shear stress, we will write a tau equal to shear stress, and other one is the shear rate, okay, shear rate here. It is very simple, okay. The shear stress then shear rate is a 2 parameter model, but if you use some other, okay, tau naught or some other, okay, variable, that we call as a 3 parameter model. Even 4 parameter model, 5 parameter model is there. Even some adsorption problem, if you look at this one, very simple, we can take like 2, then 3, then 4, 5, like that, different parameters. When you increase the parameters, it is very difficult to solve, because it is not easy and you need more this one. So if you reduce the parameters, then solving, it is always very easy to solve that one. So here this is a shear stress, then shear rate, that is the 2 parameters. When you want 2 parameter, the mathematically is very simple. Already I also discussed, if it 3-dimensional, you assume only 1-dimensional, it is very difficult to solve, but I mean if you 3-dimensional very difficult to solve, if 1-dimensional very easy to solve. Same way here, if you have 2 variables or 2 parameters, you want to solve it, is mathematically is very simple. So normally we always use the for design mixing analysis scale up the same way this one. So most commonly what are the models they use in the bioprocess engineering? Most commonly used model here. One is the power law. So the power law is the Ostwald de volume model. Then other is the Bingham plastic model. Then the last is the Kazan model. So these are the different type of model we use for the bioprocess engineering. But these all models, if it only 2 parameters, then it's very simple to solve. Otherwise, if it like 3 parameters, if you add it, then you need more to find the variables. It's very difficult to solve that one. Okay. We will discuss now what are the one by one the equation, what are the different models are here. So, the power law model, the tau equal to k, okay, this is shear rate, then n. Okay. So, the tau is a shear stress, then other one is a shear rate, so gamma is a shear rate. So, then this one is a consistency index, this one, okay, consistency index, the k is consistency index here. So, it's reflect like thickness, it's directly related to thickness. So, it's giving directly related to thickness. Then the n is the flow behavior index, it's a dimensionless. What do you mean dimensionless? Maybe okay, we already discussed also what is dimension, what is dimensionless here. Dimensionless number also there. If there is no unit, then it's always come as a dimensionless here. Okay. So, here the n behavior, the flow behavior index here, and the k is index the consistency index here. It's a very simple model, the power law model, the tau here. So, the power law model again we will discuss more on this one. So, the physical interpretation of power law parameters, what we discussed the previous model, the k is a consistency index here. It represents the resistance of flow at a unit shear rate here. Again the dimension is depends on the k equal to ml, the k whatever discussed now, the k equal to m l minus 1 t power n minus 2. Okay. So, for just assumption here, you substitute n equal to 1, then it behave as a k equal to m l minus 1 t minus 1. So, this guy m l t, it like kg per meter then second. It's always for the viscosity units here. But when you use n equal to 2, the same n equal to 2, then automatically this will get 0, then we can write only m by l. Okay, it's a kg per meter. The k always vary here, the consistency index here, the based on the shear rate. Okay. So, the next one is the flow behavior index n. It describes the already so many times we have discussed whether it's a Newtonian fluids or non-Newtonian fluids here, and also the governs the curvature of rheogram. So, here n less than 1, if it is n less than 1, it is a pseudoplastics, we call as a shear thinning, we always call as a shear thinning here. If it is n equal to 1, then we call as the Newtonian fluids here, it is a constant viscosity is constant, because n equal to 1, the viscosity not going to vary, it is a constant here. But if it n is greater than 1, we call the dilatant, it is called a shear thickening of fluids. See here the dilatant we called as a shear thickening of fluids here. When it is n equal to less than 1, we called as a pseudoplastic, the shear thinning of fluids here. Okay. So, this one, if you substitute the different value, we get the different consistency index here. So, that is the reason the k here, the k represents the resistance of flow to unit shear rate. This is a function of shear rate here, but the flow behavior index n is the whether defined as the Newtonian or non-Newtonian fluids here. So, same way we discuss here again the pseudoplastics, we discuss one by one, already discussed same thing. This is a shear thinning fluids, and then the dilatant we call as shear thickening fluid, this one. The pseudoplastic here n is a less than 1, okay. And here the apparent viscosity decreases, the mu the decrease when the shear rate get increased, we write shear rate this, okay, gamma dot. So, that definitely it is a molecular chain or cellular and the aggregates or deform under shear. Whenever apply shear, it get deformed here. So, example already we discussed, same way the filamentous fungal fermentation broth, then xanthan gum, alginate this one, then cellulose suspension, all coming the pseudoplastic. So, mammalian cell cultures, this is all in the pseudoplastic here. So, the engineering implication same we discussed already, is a high viscosity at low shear, Vu oxygen transfer limitation should be there. Then same way for when is viscosity decrease near impeller, but then we have to improve the mixing of efficiency here. The next one is for dilatant, the previous one is for shear thinning, and this is a shear thickening of fluids here, shear thickening of fluids here. So, n is a greater than 1. So, here the apparent viscosity we write mu A increases when you increase the shear rate, because shear rate if you get increased here, you apply shear rate, when you apply shear rate, so the apparent viscosity also gets increased here. So, due to the particle crowding and structure formation under shear, that is the meaning that if you apply the shear and the particle, definitely the structure formation also will get disturbance here. What are the bioprocess relevance? The example here, it is a rare in biological system, normally this type of dilatant this one, but of course, it is a highly concentrated starch suspension, but whenever the low, that is called in the other this one, the highly concentrated starch suspensions, then dense particulate slurries all come under the example of the dilatant fluids, that is called a shear thickening fluids here. The previous one is the shear thinning fluids, and here shear thickening fluids here. So, the apparent viscosity of power law we already discussed, the mu A, this is already okay, mu A equal to the shear stress, then shear rate. So, here that is a power law relation here, you just see here, if it is n equal to 1, okay, you just substitute here n equal to 1, so then mu equal to k, nothing to happen here. But when you apply here n less than 1, if n less than 1, if you apply n less than 1, so then automatically the mu A, the apparent viscosity k by some value is negative value, gamma power some minus, okay, you say minus 0.5 if n less than 1, okay, n less than 1 minus 0.5 or minus 1.5. So, whenever this shear rate get increase, so you can write otherwise this way, k by gamma. So, whenever the shear rate increase, then the mu A get decrease, that is the meaning of n less than 1. The same point if you apply n greater than 1, so then this gamma shear rate will comes to this point, okay, then mu A equal to k gamma here. So, the shear rate get increase, then the apparent viscosity also get increase, but this point is here, when increase the shear rate, the apparent viscosity get decrease the first n less than 1. So, next one is the Bingham plastic model, tau equal to tau naught, the Kp, since okay, Bingham plastic model, then gamma dot. So, here the tau naught is the yield stress, then this is the shear rate. Same thing we discussed when you apply the Bingham this one. So, up to that one is the best example for the paste, what we are using the normal the life, no, there is no flow, the tau equal to tau naught or tau equal to that value, okay. But when you increase the tau naught value, then the flow starts here. So, I already discussed, no, the flow starts here. So, up to this point there is no flow here, but once it cross above tau naught this one, then definitely the value shear rate value get increase here. That is only we are mentioning here tau equal to tau naught, then this nothing will happen here, there is no flow here. But after that they behave as a Newtonian fluid, same thing what we discussed here, after some time they behave as a Newtonian fluid here. So, what are the best example here? Same way, activated sludge process in wastewater treatment, then the bacterial paste here, then the highly viscous the fermentation here, already we discussed same way. So, then another last one is the Kazan plastic model, is a root of tau naught here, it is always behave as a, after some time post yield this behave as a pseudoplastic. You just see here, the previous one is behave as the Newtonian fluids, but when you increase this one, then it behave as a pseudoplastic here. And the example type of this one, the blood rheology always we use here, then chocolate and then lipid protein dispersion all will use here. The structured biological suspense all under the come as the type of Kazan plastic model fluids. So, what are the engineer significance of bioprocess design now? If you want the choice of rheological model, definitely what are the it will affect here the power consumption, if it is Newtonian or non-Newtonian here. Then next one is for oxygen, the nutrient mass transfers. Then next is the impeller and agitator selection, that also main thing here. When you want to scale up, and definitely the choice of the rheological, this will affect here also. So, if you assume again Newtonian, I already discussed same way, it is a oxygen limitation, we are not thinking that one, then definitely it will reduce the productivity, because it is already this non-Newtonian, but you are assuming as a Newtonian. So, then we will definitely affect our the productivity this one. Thank you.